Hi, and welcome to the first section on resampling strategies. So our learning goals for this section here are understanding how resampling techniques extend the idea of simple train test splits, so simple holdout splits, and that they are simultaneously allowing us to reduce the pessimistic bias of a single holdout split and also additionally to drive down the variance of the performance estimator. I'll furthermore introduce here the basic ideas and the basic methodology of resampling strategies like cross-validation, like the Bootstrap and Subsampling, and we'll begin to discuss some simple properties of them. And we'll talk a little bit about stratification on top of that as well. Let's remember what our goal in machine learning evaluation actually is. So we want to estimate the generalization error. So this expected loss here when we run our training algorithm on data sets of a certain size, so for size n, and then run our inducing algorithm on such a training data set and evaluate it through fresh test samples xy, and then measure expected loss. So this is the theoretical definition. So expected generalization error for a certain learning algorithm, and in this expectation we would now average out over the training data and over one independent fresh test sample. And we've also already discussed that in practice this leads to a problem because we would like to estimate this here for our given n. So if we have a data set of 1000 observations, we're going to fit at the end a model with n equals 1000. Well, we're going to fit a model on that complete data set. So we want to estimate the generalization error for that model, or at least for a model fitted on data of exactly that amount. Now, in practice, we can't do that because we've also already discussed that we can in practice only evaluate models on, or at least we think that we can evaluate models in an unbiased fashion only on new, untouched test observations. So in single holdout splits in our estimator, the size of the training data set will always be somewhat smaller than the size of the complete data set. And because of that, there's a pessimistic bias going on in holdout splitting, and the smaller our training set actually is in our split choice, the higher the pessimistic bias will be. Of course, if we make our training set extremely large, then there will be only very, very few data points left for our test set, and the smaller our test set becomes, the higher the variance of our generalization error estimator becomes. And this seems like a super annoying and super bad trade-off, because both of these things are bad in order to produce a good GE head estimator. Fortunately, resampling is a very, very nice way out of this problem. So in resampling, we repeatedly split our training and we repeatedly split our original data set in training and test sets, and then average results. So that's the basic definition. So pretty simple. So in a certain sense, we run holdout multiple times. The good news is that because of these repetitions, we can now allow ourselves to have pretty large training sets and hence only have a very low pessimistic bias in our estimator going on. And well, if we now have that low pessimistic bias, the variance would be quite large, right? Because our test sets are super small. Yeah, but fortunately, that variance we can now easily drive down by averaging over many repetitions. In each single iteration of resampling, we might only look at, 10% or 5% of our original data set, and that single estimator might have a high variance, but because we kind of, I'm not sure what I want to say, independently repeat. I'll discuss this in the second section a bit more, whether these things are really independent or not. Because of these averages, because of these stochastic averages, our variance gets reduced considerably. So here is how that is defined mathematically. So we can now represent training and test sets by index vectors. So I have a JTrain index vector for one given training set, just a bunch of indices which tell me which observations from my original data set D, which I might represent as 1 to n, go now into the specific training set, and which observations go into the test set, again represented as an index vector. And the resampling strategy, all of these splits I can simply see as a collection of splits. So 1 and to usually capital B. That's usually my notation for number of resampling splits. And the resampling estimator looks now a little bit ugly and lengthy, but in a certain sense, it's simply one holdout estimator for the first split and another holdout estimator for the second, and so on. And then I aggregate all of these holdout estimators together. And usually this aggregation means compute the mean. And usually all of these resampling strategies are constructed in such a way so that this n train here, or the size of the training set in each iteration, they are roughly or nearly exactly equal. And the reason for that is because like I've said before, I want to argue about the performance of a learning algorithm when fitted on a certain amount of data. And if these are all super heterogeneous in terms of size, it doesn't really make sense anymore. So I usually construct them in a manner so that I always use in each split, I don't know, something like 80% of training data. And here's our first and also most popular resampling strategy. It's called cross-validation. It's also quite easy to explain. So we take our complete data set and we split it into nearly equal, or if possible, equally sized partitions. So in this case here, I have visualized this for threefold cross-validation. So this would be my complete data set. Maybe this is, 900 observations, and then I split it into 3 parts of 300 each. Now my threefold cross-validation would have 3 iterations of holdout estimation, and in each iteration, one partition becomes the test set exactly once. So here in this first iteration, this guy would be the test set, and then these 2 guys would take on the role of the training data. So they get joined, they get merged. I train my model on these 2. I predict on this guy here. I estimate with my performance metric rho, and that gives rise to my first test error, or my first generalization performance number. And then I do the same in the second iteration, and now maybe this guy here becomes the test set. I do exactly the same. And in the third iteration, this guy becomes the test set, and I get a third performance value, and at the end, I average those. So I obtain k test errors, and I compute their mean value. And that's cross-validation. We can also easily figure out how much data is used for training. So how strong how much we have reduced our training data in percentage points, which then gives rise to this pessimistic bias. So if we would use a 10 for cross-validation, we would always use 9 parts for training, which means we have 90% of our original data used for training our models, for producing our models. So we are reasoning, we want to reason about a model that has seen 100% of the data, but we are using models that have seen 90% of data. So we are not that far off. For 10-fold cross-validation and for 5-fold cross-validation, we will have 80% of data used for training and then 20% for testing. Be careful here in terms of how much is used for testing. So it's not really only 10% or 20% in 10 CV or 5 CV. In cross-validation, each observation is tested exactly once. So in a certain sense, we're averaging over all of the observations from the original data set and computing their loss and averaging that in a manner where all of these observations, when they are tested, they haven't been used for training. Here's a little extension of cross-validation that's sometimes important if you have to handle imbalanced data. So the usual example is when target classes are quite imbalanced. So I have one super simple example here for visualization purposes. So we have the blue class and the orange class, and the blue guy is larger than the orange guy. And in such cases, if I now randomly split up my data in 3 parts, then it can happen that this orange class, which is already very small, now becomes even smaller in certain training and test folds, and that can lead to problems and artifacts in the estimation. So to discuss a very extreme example, so for example, the orange class might be so small that through unstratified cross-validation, now there are so few orange points left in a certain training fold that my model completely ignores the orange class when it's being fitted. And our way out is a pretty simple one. So we usually try to preserve the distribution of the target variable. We can also do this for other features. So we could also do that for input features. I don't know, maybe there's an input feature gender, and for some reason we didn't have, I don't know, too many females in our study. And we also want to stratify now over the gender variable to ensure that these are equally distributed in all of our training and test sets. And stratification can be used for that as well. But let's keep things simple here and define this for target classes in multi-class classification. So what we would then do is that we don't run a normal cross-validation, but we basically run our cross-validation multiple times in terms of the partitioning, not in terms of the estimation. So we would run the cross-validation splitting procedure one time on the first class, and then again on the second class, and maybe if there's a third or a fourth class, we also equally partition those guys. And then when we want to construct our first split, we merge these two together, and this would be our the data for our first global CV. And we also merge these two guys together, and we merge these two guys together. And then if we do that, I hope you can easily see that simply by construction in each fold, in each partition, there will be exactly the same amount of data points for the orange class and for the blue class. For the orange is more important because the small one. And let's not say exactly, but it's as equally distributed as possible. If you have super small sample size problems, there might be minor differences. Some short discussion of cross-validation and some first recommendations. So 5-fold or 10-fold for cross-validation are very common because of this 80% or 90% in training data. So this is usually used for, let's say, data sets of medium size. So somewhere between 1,000 and maybe 100,000 observations. 5-fold or 10-fold cross-validation are very common. There's also an extreme case, which is known as leave one out. And this is a technique for very small data sets. And leave one out cross-validation means that the number of folds is exactly n. And this means, each fold consists of exactly one observation, and we leave out one observation exactly once. Of course, that implies we have to fit and test n models, so this might become rather expensive. We can now also discuss a little bit more the bias of the cross-validation estimator. I guess we have done this already a little bit. So the more folds we use, the smaller the bias becomes, right? Because of this k minus n divided by k fraction that's used for training. So for 10-fold cross-validation, we have 90% of data being used for training. So we have a quite small bias. If we would opt for leave one out, we would call that nearly unbiased, because we have really now n minus 1 divided by n. So if n is not super small, this will be very close to 100%. And here's a word of warning. So leave one out has been recommended for small sample size situations. So I don't know, for data sets of, let's say, 200 observations. But this estimator itself has a quite high variance, and this is a little bit more difficult to understand. And I'll not discuss this here in this section. Discuss this in another deep dive, but at least I want to mention it here. So for small sample size situations, it's usually better to use a high number of folds in cross-validation. That's certainly true, but not go to the extreme end and use leave one out. And in a certain sense, that's also better in terms of computational efficiency. So do something like leave 5 out, or something like this, but not leave 1 out. And an even better estimator is usually to do something like leave 5 out. I use a 20 or 50-fold cross-validation, but even repeat that. That's called repeated cross-validation. Its definition is extremely simple. So we just run one cross-validation with a certain random partitioning, and then we run another one with another partitioning, and another one, and another one, and another one. And at the end, again, we average all performance estimators. So this is sometimes called 10 times repeated 10CV, or it's not called like that. That's a standard approach for very small data. Here's another strategy that is also sometimes used. That's called subsampling. Very easy to define. So subsampling is simply repeated holdout. And of course, again, we average performance estimators again at the end. Some people also call this Monte Carlo cross-validation because of this, more, let's say, random splitting approach than the more structured one in CV. Typical choices for splitting, for the splitting rate, so how much data goes into training or testing, is pretty much similar as for cross-validation. So we often use 80% or 90% of data points for training. And again, the smaller the subsampling rate, the larger the pessimistic bias. The more repetitions we use, the smaller our variance will become. So if you want to produce a very good estimator, take a very large subsampling rate. So I don't know, 95%. But of course, then you have to also use a very high number of repetitions to again ensure that you have tested everything that's in the data set, that you've used all points for testing. Last variant here, the Bootstrap, last basic variant, the Bootstrap, similar to subsampling. This is also a stochastic technique where we draw B training sets, but now of size n, so of exactly the size that we want to produce our estimator for. That's kind of the idea behind Bootstrap, to not always reason about training data sets which are too small and which kind of by construction now carry this pessimistic bias with them. And of course, that's kind of only possible if we sample with replacement from the original D. And our test observations now will be all of the out-of-back points that we haven't drawn into our training data set. You can see this here, right? Maybe we have these 4 colored observations here, red, green, blue, and black. And then here we produce our Bootstrap in-sample training data sets, and you can see the replications happening here for example, for this guy. So the red guy would now be in there twice. What's our test data for this? So it would be just 1 point. It would be the green guy. Yeah, and here this guy is replicated, and I guess for this super small example, I have only apparently 1 out-of-back observation. So for this guy, it's the black. And we can perform a similar analysis as for subsampling. So the more repetitions we actually perform, the lower the variance of our estimator. We can also now reason a little bit about how many unique points will actually be there in our training set now, because it sounds a little bit like Bootstrap would be completely unbiased, so would have no pessimistic bias at all. That's kind of the idea behind this. Unfortunately, this is really not true, because we can't really assume that we're going to learn as much from these repeated points as we would from these replicated points as we would learn from true IID, true unique samples in the training set. But let's do the computation first. So that's not very hard. So we can now compute the probability of an observation not being in the training data set, and then you do 1 minus of this. So to figure out how many points are unique in the training data set. So what's the probability that a point is not drawn? This is 1 minus 1 over n for each point. And then we have to do that for every sample. So raise that to the power of n, and then do 1 minus of the thing. And from elementary calculus, we know if we let that here go to, if we let n go to infinity, this is the very, very well-known limit. And this is exactly e to the power of -1, or 1 divided by e. So and if you then calculate this, this is roughly 2/3. So this is the approximate amount of unique points we will see in our training data set of size n. And there's another problem that Bootstrap is not so popular anymore nowadays in machine learning performance estimation, and this is that these replicated training points can actually lead to problems during fitting into certain artifacts when running machine learning algorithms. So some algorithms actually, let's say, react in a somewhat unfavorable manner to these replications being in there if you don't kind of use specific variants of certain learning algorithms. So usually you sometimes have to do something extra to handle this, and we sometimes dislike these artifacts and problems that result from these technical replications. It becomes especially bad if we use Bootstrap as a resampling procedure in hyperparameter optimization. I also want to mention here, for completeness sake, that there are some extensions of the basic Bootstrap. So the B632 and the B632 Plus are made for small sample size situations. They have both been invented and studied in depth by Efron, and they also use actually the estimator of the training error, where we until now have said that this is kind of forbidden in machine learning to use that for performance estimation because it can become so small. To in order to try to produce a better estimator for very small sample size situations, of course, we have also discussed that unfortunately the training error for complex model classes can actually become 0. And then the B632 basically produces a convex combination from the testing error and the training error. And this, for many model classes in ML, this kind of leads to a direct underestimation because of our training error, because that can go down in a kind of unrestricted way directly to 0. So in B632 plus, what actually is being done is, before we do the convex combination of the training error and the test error, we compute something like the overfitting rate of our model or of our learning algorithm. And then the more we actually overfit the training data, the more we downweight the training error in the convex combination. But I don't want to go into these details here. For us, it's enough if we understand the basic Bootstrap. These extensions are not part of this basic section here. So I want to end with one also not unimportant meta strategy in resampling for situations when we have multiple observations from the same object, because that happens in practice, unfortunately, quite often. So for example, we have multiple observations from a single person. So maybe, I don't know, measurements from a person, longitudinal measurements over multiple days, or we have certain observations from different hospital sites. So there's maybe data we have collected from 100 hospitals, or we have smaller images created from one base image, and then one machine learning observation would be based on this smaller partial image. Now our data is now not IID anymore, so in a certain sense we are already violating one of the fundamental assumptions in ML, and one can also now discuss what one would have to do in terms of modeling. And there are also variants and approaches for improving our our machine learning models themselves. What I want to discuss here is how we should evaluate, so independently of what happens inside of the learning algorithm. And it seems to be pretty clear that a good strategy now would be to take all of the observations from one object and place them either completely into the training set or completely into the test set. Because what we don't want to do is have, parts of the data from one object now in the training set, overfit to that, and get a biased performance estimator, because some of these observations would also be part of the test set. So if we don't do this, if we would, kind of randomly distribute them, I would guess that, I wouldn't guess, it's quite likely that in many of these situations we would now produce an optimistically biased GE hat performance estimator. But the way out is also somewhat simple. So we usually now run cross-validation on objects, not observations. So these instances, so these hospitals or these persons, or in the extreme case, we could leave one object out. And we have visualized this down here for 3 objects. So this purple, yellow, and greenish guy here. So this would be one instance, one object. This would be the second, and this would be the third. And we could now run a 3-fold cross-validation on the objects, where in the first iteration, this becomes the test set. In the second, this becomes the test set. And in the last one, this becomes the test set. And then we constrain our splitting to these instances. And as long as we have not too few of these, this should work out reasonably well.